Okay, everyone, what we're going to do in this video is we're going to go over inductance, okay? This is not necessarily a new concept for us. It's something that we've already been playing around with, but we want to formalize the idea of what this is now and add a little bit more depth and detail to it. So, by now you guys are familiar with the shape of a solenoid, right? So the reason why we coil wire in this way and then run current through it is to generate a magnetic field. You guys have seen this, right? So if I use my right hand rule with my current, then I can generate, so I can see that I will generate a magnetic field inside a solenoid with this direction, okay? I'm going to put this out here. Okay, but remember that my electric field and my magnetic field, they're linked to each other. We've already sort of been discussing this already, where my electric field and my magnetic field are linked by the fact that if one changes, you will generate the other. Okay, so the first time we saw this was that in the case where we have current running. So what we're doing when current is running is charges are actually moving, right? Electrons are physically moving through space. And so when they do that, when they move, the electric field around them changes, and that generates a magnetic field. So that magnetic field is generated here. But we haven't explored too much yet the fact that if I change my magnetic field, so if I have some magnetic field change, I will generate an electric field. I will generate some electric field and it'll look the same. It'll actually look the same if we kind of draw out, one side of a magnet. Let's say this is a north-south of a magnet. And I move this magnet. So I take my magnet and let's say I move it back and forth in space. Then I'm changing the magnetic field in space, right? Because initially it was here, okay? And then I move it, so now it's, it's here. And so I'm moving where these vectors are in space. And when I do that, I'll actually generate an electric field and it'll look just like before. It'll look like a rotation, right? It'll look like a loop around my magnetic field. It's just the mirror of what happens when you change an electric field, okay? So this idea of inductance has now come in because the only thing we haven't really explored before is that when I create this magnetic field in my solenoid, I'm getting a change in magnetic field, right? So because I'm creating a magnetic field, that change in magnetic field will create its own electric field. Let's see what color I can use here to describe this. Let's go ahead and put the screen color here. So when I create this magnetic field, I'll actually create an electric field. Okay, while I'm building up my magnetic field, I'll create an electric field. Okay, but this electric field, should have drawn it the other way. My loops actually go the other way, but this electric field runs counter to my current. So what will actually happen is that this will impede my current. Okay, current flow. So this impedance of my current flow means that it's going to be difficult to run current through here. So you try to run current through, it creates a magnetic field. That creates an electric field in the opposite direction that's fighting against you. And so current is very difficult to run through this wire. You have to push hard with more voltage in order to get it to go through. But this is only in the beginning when you are creating this magnetic field. Once you do this for a while and my magnetic field stabilizes, then this electric field goes away and then you just normally run your current as you normally do, right? So when we put these this kind of element, this solenoid in a circuit, what'll happen if I put this in a circuit and then I try to run current through, it will, at first, it'll slow down. It won't let any current through at the very beginning, but then slowly the current will rise, right? So I'll get my current kind of rising up until I have some, okay, this will be current, this will be time. I'll have my current rising up over time until it gets to some maximum value. But in the beginning, when I first connect this circuit, no current will actually flow because my magnetic field change will be very strong in the beginning, so the counter field that it makes will kind of stop it. So this is actually a really good element to have in a circuit that feeds current into the circuit slowly, right? Which might be a good thing for safety, right? It might be good for safety of the actual other components in the circuit, but it also just changes the dynamics, the timing of the circuit in a way that lets us have more control over what goes through. And we'll talk about that in a future lesson. Okay, so this is called self-inductance of a solenoid, right? The solenoid, when we run current through it, will create its own inductance and because of the change in its own magnetic field. And the way that we model this here in a solenoid, the self-inductance, this is L, capital L is going to be my inductance with unit Henry. I know we're getting a lot of units now, okay? We've got a big list of units and formulas, so it'll take a little bit to put them all together and keep them all in order, but I want you guys to focus on keeping this information organized if you can. Okay, we've got our trusty permeability constant right here. This is still number of loops. So this is number of loops. This here is the area of a loop. Okay, and then this here becomes the length. I know I used capital L before, but now we're changing it to lowercase l because we have now our capital L is inductance, right? So here is our formula, number of loops, area of a loop, and length of my solenoid. These things will determine the self-inductance, right? How much of an inductor is this solenoid, okay? So this change, inductance, will induce some sort of voltage, right? It'll induce some sort of potential, some EMF. And this is usually counter, so we have this minus, it's counter to whatever the voltage supplied to it is. So what we have here is just a quick, derivative formula to show that the change in flux, the change in amount of magnetic field going through this over time is going to induce some change in my EMF, okay? Or it's going to induce an EMF on its own, right? So we have here an expression for this, which is given by also number of loops. Okay, so same thing. This is also number of loops. If we wanted to find just how much of this voltage is induced here, okay, this is still my magnetic field. And this here is my variation of my wave versus time. So basically, this is going to work when we are changing our voltage source over time. Whatever kind of current that we put in here, current signal, it'll generate some EMF based on its change over time, right? So it's the change of my flux over time. So I'm just going to model this here with how much the angle is changing over time, right? So this is a useful formula for us to kind of apply to circuits. We're not going to focus too much on our EMF formula here. What I want to do mostly is introduce you guys to self-inductance of a solenoid, because this concept is going to be very important when we start to talk about circuits that include inductors in them.